Thanks for attending this presentation on justification for power laws and the fractional models. And the questions I'm starting with are whether fractional wave equations give clues to some deeper reality, or if they are just some compact phenomenological description. That's a question that I posed in my book last year. And also whether there is a common underlying framework for power laws across applications, medicine, sediment acoustics, or if each application is unique. I'm going to be starting with some attenuation mechanisms from standard acoustics. That's heat relaxation, where inner and outer states of vibration in molecules and liquids. There is an exchange of energy between these states. That's structural relaxation, where small and large clusters of water molecules, for instance, are perturbed by a wave, small and large clusters of ice, if you like. And there's also chemical relaxation, which is prominent in salt water, for instance. Now, I've been trying to find fractional or anomalous parallels, and heat relaxation has a parallel in anomalous heat diffusion. Multiple relaxation and hierarchical models may be looked upon as parallels to structural relaxation. And there is also a vague chemical analogy. Then there are some unique ones like non-Newtonian rheology and turbulence in poroelastic models. Those two last ones are relevant for sediment acoustics. First, anomalous heat relaxation. Now, there is a Newton's law of cooling that says that the temporal change in temperature is proportional to the absolute temperature. So, and that describes heat convection from a warm surface to a surrounding cooler fluid, and describes diffusion in a thermal boundary layer as a result of Brownian motion of particles. That can be rephrased in what's called anomalous diffusion, where there is non-Brownian motion of the particles. This is done by making the derivative a fractional derivative, gamma between 0 and 1. It's been done by several people, but I'm going to start with what Manardi did there. Now, this can be used in a rather elegant derivation of a fractional Zener model, starting with temperature expansion, and that's included with the normal Hookean elongation due to stress. And then the Newton's law of cooling, we are adding an adiabatic expansion term to that one as well. So changes in strain will result in temperature changes. And now forget the fractional one initially, but if we combine these two, eliminate delta T, we'll end up with a Zener model, the standard linear solid model, which is one of the fundamental models for material properties with viscosity. That was done by Zener in 1948. Now, if we do that with the fractional version, we will come to the fractional Zener model instead. Manardi did this in 1994. And I think this is rather interesting how it connects anomalous diffusion to this material model, fractional Zener model. Now, how to use that, how to move on from there, I'm not so sure, but at least it's an interesting observation. Moving on to hierarchical models, then these are prominent in biomedicine. And here's an example. If you measure the cell share modulus, like here, over 1, 2, 3, 4, 5 decades of frequency, or actually 3.5 decades of frequency. And then you observe that this share modulus looks like it has sort of two power laws. Smaller slope initially, and then a higher slope for higher frequencies. So it's even more visible in this paper, which covers more decades of frequency, and shows even more clearly the two power laws. 0.005 for low frequencies, 0.75 for high frequencies is quite typical. Now, what can cause this? And here we only have some vague notions of that, but we can think of it as coming from hierarchies of smaller and smaller systems. So in Colligan, there's something like 5 substructures, which can explain some of this, but not all of it. And so often for complex polymers, we use a ladder model like this, which is another way of writing a multiple relaxation model. The same substructures are in cells. We have 3 substructures in the membrane, the cortex, and cytoskeleton, and the last one can even be subdivided into 3. So there are several layers of submodels here. And to go to even more complex models, then the Arrhenius equation is a soft glassy rheology model, which encompasses even more of that. The rate constant, sometimes associated with these models of a chemical reaction, shows that there is this exponential relationship between the activation energy for the reaction and the absolute temperature. And interestingly, if we let the activation energies be distributed uniformly, then we'll get the logarithmic spread of the relaxation times. And that is something we'll be using in fitting multiple relaxation processes. Now, so that brings me to my next point, multiple relaxation, closely related to hierarchical models, actually. So then we're talking about models like this, where you add the spring dampers each for each process. Attenuation can be shown under some conditions to be a sum of contributions weighted by this A sub nu and the characteristic relaxation frequency. And if we let all the weights be unity and we add up these things, these contributions, we spread the relaxation times logarithmically, as sort of hinted at from this Arrhenius equation. Then, if we have a power law to the power 1 and we want to approximate it by relaxation functions, we get the blue result. So it's sort of, we have 5 evenly spread the relaxation frequencies in logarithmic frequency. And we cover something like 1, 2, 3 decades or so of frequency with the power law in this case. So there is a way of doing this, and actually it can be shown that if we take a fractional Zener model which has power laws, and we find the equivalent distribution of compressibilities that corresponds to that, it has a distribution that looks like this. It has a power law tail, it has a power law initial part here. This is as a function of relaxation frequency. And the power law tail indicates something like scaling variance. Its approach, it's a single power law as alpha goes to 0, this dashed red one. And that's the case for attenuation, which follows omega to the power 1. And you can show from this that the weighting in the previous examples should be proportional to the relaxation frequency to the power of alpha, which gave unity weights in the previous example. So this can be used in another example where we want to now fit omega to the 1.3, not the 1.0. The same logarithmic spread of relaxation frequencies marked by these dots. And we weight it to approximate omega to the 1.3. And this procedure is used for simulation in medical ultrasound and can be used to interpret the extended Buol model as well. And I'll come back to that. So it seems like if we spread, if we weigh contributions to a relaxation sum like this, we can find the equivalent of a fractional wave equation. It's actually an infinite sum. So there is infinitely many processes, not just the 2 of air, and nitrogen and oxygen, or the 2 of salt water. And the way they are distributed is somewhat, there is something fractal about this, is scale invariance. And it tells us something which I don't really quite know what means yet, but maybe we'll figure out. Next point, non-Newtonian rheology. This is related to grain sharing, the model of Buckingham. So if we have a consolidated sediment like this, and there is stick-slip intergranular elastic behavior when grains of sand sort of slide against each other, and there is a pore film, then this can be modeled. This is what Buckingham showed. He called it strain hardening, and it can be modeled as a spring in series with a time-varying damper. It's also called time-dependent non-Newtonian or rheopectic process, which is what we called it in our analysis of this. And this has an analogy in fractional derivatives. And that actually means that if we take the quite complex compressional and shear wave equations from Buckingham, where he has this operator which is convolved into the loss operator here and into this term here, it can be shown that the pressure wave equation is a fractional Kelvin-Voigt wave equation, lossless terms plus a fractional loss term, alpha equals 0, and it becomes the viscous wave equation. And the shear wave is a solution wave equation is a fractional diffusion wave equation, where alpha equals 0 gives us a lossless wave equation, alpha equal 1 gives us a diffusion equation where there is no propagation. And that is for grains that are not in contact with each other where you have no shear wave propagation. So this is one of the closest results I've found between fractional descriptions and actual physical models. So the basic grain sharing theory is related to standard fractional wave equations. Now it's been extended with viscous grain sharing theory and so on. That's not so simple, but I analyze that in chapter 8 in my book. Last point here is the pore elastic models. And we've tried to do the same thing with the BO model, so this extended BO model, and tried to interpret it in terms of multiple relaxation and fractional models. Now, this model, which comes from Shaziris and Isaacson in 2014, has properties from the BO modified gap stiffness model, the BO with the contact squirt flow and shear drag, and the squirt flow model. And we found that the fast compressional wave has one spring damper model for low frequencies, one for high frequencies, covering pore viscosity, bulk relaxation, shear relaxation. In the high frequency case, the dampers are transformed to fractional dampers of order half. And the same is the case for the shear wave. There is a similar model with one less term for pore viscosity, bulk relaxation, shear relaxation, and fractional models of order half for pore turbulence and bulk relaxation. And so even here, there is quite a close connection between multiple relaxation and fractional models and these extended BO models. And the extended BO model and the viscous grain sharing models, those are the two main models for sediment acoustics. So where has this taken us? Well, it's taken us to explored some parallels between standard and complex media. And what about our questions? Well, I'd say that we are closer to understanding the link for sediment acoustics, not so close for, here is an ultrasound image of a kidney and the fractal tree, not so close for that case. And since that's the topic of this session, that's a pity, but at least we've made some progress for the sediment models. So thank you for your attention.